Greetings to all. My name is Zinziposha Kakai. I hope and trust that everyone is doing well, especially in this current climate. So today I'll be presenting a technical research paper titled Global Patterns in the Vulnerability of Ecosystems to Vegetation Shifts Due to Climate Change. So this paper was written by Patrick, Ronald, James, and Raymond, and it was published in 2010 under the Global Ecology and Biogeography Journal. So the main aim of this research was to identify areas vulnerable to vegetation shifts and potential biome changes. It was based on global vegetation biomes. I think it's safe for me to assume that everyone understands what climate change is and how it affects species. So allow me to add on to your knowledge. Climate change is shifting vegetation latitudinally and elevationally in boreal, temperate, and tropical ecosystems. Changes in climate have changed plant mortality and recruitment by suppressing physiological thresholds and altering wildfire and other disturbances. The replacement of dominant plant species can completely evolve the biome of an area and shift the global locations of biomes. These basic changes can modify ecosystem structure and the provision of ecosystem services like water, availability of water resources, and firewood to people. Analysis of novel future climates and simulations using global vegetation models have projected future shifts in climate and vegetation due to climate change. So the picture below illustrates how species respond to increasing temperatures, and they are most likely to move towards regions that are cooler. To explore the application of spatial analysis of climate and to identify biomes that are susceptible, ecosystems that are susceptible or vulnerable to biome changes, 3 sets of potential indicators of the vulnerability of ecosystems to biome change were examined. So the researchers first looked at the observed changes of the 20th century climate, followed by the projected 21st century vegetation changes using a GGVM under 3 IPCC emissions scenarios, and lastly the overlap of results from point 1 and point 2. The IPCC uncertainty criteria were used to develop a vulnerability classification framework that could be used to identify priority areas for adaptation measures. Climatic and ecological evidence supports the use of observed climate as a potential indicator of vulnerability of ecosystems to biome change. So some of the evidence shows that comprehensive meta-analysis of published ecological research demonstrates that climate change in the 20th century has shifted plant ranges and phenology in ecosystems around the world. Because vegetation often responds slowly to changes in environmental conditions, a time lag between a change in climate and a shift in vegetation can commit an ecosystem to biome change long before any response manifests itself. With that said, future vulnerability is partially a function of past climate change. So to quantify potential indicators of vulnerability, the IPCC definitions of likelihood, confidence, and vulnerability were followed under methods. So firstly, likelihoods of observed changes of 20th century climate from probability density functions of 102 years of observation data were estimated, followed by the confidence levels of GGVM projections from the output of a set of different general circulation were also estimated. Here, vulnerability is the susceptibility of an ecosystem to a change in its biome. Vulnerability is a function of 3 components: exposure, sensitivity, and adaptive capacity. In this analysis, observed and projected climate changes indicated a degree of exposure. Deviation of climate from long-term mean values and modeled changes of future vegetation provide indicators of ecosystem response, which combines sensitivity and adaptive capacity components. In the IPCC treatment of uncertainty, confidence spans 5 levels, ranging from very high to very low. These levels were used to divide results into vulnerability. For equal area projection of spatial data, To accurately calculate land areas, all global files of climate, vegetation, fire, and population data were divided into 6 continental files, and each continent was projected to lambda azimuthal equal area projection at a spatial resolution of 50 kilometers. So data covered the terrestrial area of the world except for Antarctica. For observed climate and fire, the observed climate trends were calculated by linear least squares regression of mean annual temperature and annual precipitation versus time for the period 1901 to 2002. The statistical significance was also calculated for the correlation coefficients. The statistical significance does not give a direct measure of the magnitude of the change. So a variable or a factor can be statistically significant, but that does not necessarily mean that we do not reject the null hypothesis if need be. For each of 58,267 land pixels, the following was calculated. So the rate of observed temperature change expressed in degrees Celsius per century, followed by the fractional rate of observed precipitation change per century, and lastly, the probabilities of the observed climate changes were calculated. So the subscript that you see in the equation here denotes temperature or precipitation. This formula was used to calculate the probability that the rate of observed temperature change or the fractional rate of observed precipitation change falls within a calculated number of standard deviations of the mean. So the value of P that was greater between temperature and precipitation was used for interpretation and classification purposes. The pixels were then classified into 5 vulnerability classes. So to model potential vegetation and wildfire, the MC1 dynamic global vegetation model was used, and the MC1 dynamic global vegetation model uses 5 climate variables, namely monthly mean, maximum and minimum temperature, precipitation, and water vapor and vapor pressure, and 5 soil variables: soil depth, bulk density, clay, sand, and rock fractions, to run interacting modules of biogeography, biogeochemistry, and wildfire. The biogeography module identifies the potential vegetation type of a pixel by modeling plant life form as distinguished by leaf characteristics. The biogeochemistry module calculates the biomass of trees and grasses for each pixel by modeling net primary productivity, organic matter decomposition, and carbon, nitrogen, and water cycling. Lastly, the wildfire module simulates wildfire occurrence and behavior based on fuel loadings and fuel and soil moisture. Potential fire here was modeled with no human suppression. To assess the accuracy of MC1, its output was validated against observed global vegetation and fire data. Here, areas of forest and non-forest modeled by MC1 dynamic global vegetation were compared to those derived from remotely sensed data. For each of 54,433 land pixels, the level of confidence in projections that the biome of an area may change was estimated. So the pixels were further classified into 5 classes of vulnerability based on the level of confidence in projections. Population. So in order for the researchers to have an idea of how many people would be affected by the changing biomes, they estimated the human population living in each vulnerability class, and data was acquired from the Center for International Earth Science Information Network, and it was masked by the area of each vulnerability class to calculate the total number of people living in each area. Results. Observed changes in climate and fire. So temperature increased on 96% of global land in the 20th century, with significant increases on 76% of global land. The average temperature increased on every continent, with the greatest warming occurring in boreal regions. Precipitation increased on 80% of global land in the 20th century, with significant increases on 28% of global land and significant decreases on 2%. Regions like the West African Sahel experienced the greatest decreases in precipitation. Furthermore, fire frequency in the 20th century decreased on 2/5 of global land. Decreased fire across regions like Australia, North America, and Russia shows extensive suppression, while increased fire across the tropics shows increased burning to clear agricultural fields. So due to these human influences, only observed temperature and precipitation were used as potential indicators of vulnerability. So for vulnerability, observed climate and vegetation projections indicate that 1/10 to 1/2 of global land may be highly to very highly vulnerable to biome changes. So an overlap identifies areas that are highly to very highly vulnerable. Some of these areas are Boreal Canada and Russia and Southern Africa. So these results are in agreement with the temperature map that you have seen on the previous slide. Temperate mixed and boreal conifer forests showed highest vulnerability. Tundra and alpine and boreal conifer forest biomes were most vulnerable. Deserts showed lowest vulnerability, and lastly, the tropical evergreen broadleaf forest was least vulnerable. Approximately 3 billion people live in areas of high to very high vulnerability under observed climate only. So this is about half of the world's population. Approximately 800 million to 1.3 billion people live in areas of high to very high vulnerability under the other cases. The other cases being the interaction of observed climate and the projected change in potential vegetation. For discussion, we have global vulnerability. So observed climate changes signal high vulnerability for almost half of the global land area. Vegetation projections suggest potential latitudinal biome shifts of up to 400 kilometers, consistent with projections of individual species range shifts. Temperate mixed forest shows high vulnerability as a fraction of biome area due to projected loss of coniferous species and potential conversion to temperate broadleaf forest. The tundra and alpine biome shows the greatest total area of high to very high vulnerability due to elevated rates of both observed and projected warming. So the graph here on my right hand side shows a percentage of area that is vulnerable according to observed climate and projected changes in potential vegetation as well as the overlap. Rainforests are resilient to biome change because of high temperature tolerances and mitigation of water stress by increases in equatorial precipitation, as well as the wide latitudinal extent of woody plant species. The DGVMs project a shift of boreal forest into tundra at high latitudes and some forest loss in Amazonia. Projections also show forest changes in the southeastern USA and East Asia. There is a projected increase of wildfire in the Amazon, Australia, Southern Africa, and the Western USA. Lastly, a large part of the world's population lives in areas of potential biome changes, and this will have an impact on the provision of ecosystem services and, as a result, affect the livelihoods of many of these people. Limitations of interpretation. So, to produce results at a spatial scale useful for assessing potential impacts of climate change on vegetation, empirical statistical downscaling was applied to the COS GCM output. The use of the biome as a unit of analysis may understate vulnerability. This is because the broad definition of a biome allows for changes in species composition without conversion to a different biome. The analysis does not explicitly examine reductions of tree density that may occur in episodes of forest dieback without changing the biome of an area. This further understates vulnerability. Survival and dispersal capabilities of species, human barriers to dispersal, interspecific competition, evolutionary adaptation, changing pests and pathogens, and other factors will lead to biome changes occurring at varying rates. With that said, global terrestrial vegetation may continue to change long after climate stabilization. Discussion. Adaptation of natural resource management. So climate change is inevitable, and there's nothing we can really do about it. The only thing that we can do is apply mitigation measures as well as adaptation measures, so as to ease the way we will survive or cope with the increasing temperatures. So adaptation, according to IPCC, is an adjustment in natural or human systems in response to actual or expected climatic stimuli or their effects to moderate harm or exploit beneficial opportunities. Researchers sought to develop a vulnerability analysis framework with clearly defined classes to be easily interpreted by natural resource managers. They will provide data to help prioritize existing and future national and regional forests, parks, reserves, and other natural areas for adaptation. To identify geographic priorities under climate change, managers can broadly consider three options: areas of high, medium, or low vulnerability of ecosystems to biome change. In conclusion, for acquisition of new areas, it may be prudent to prioritize areas of potentially greater resilience and to avoid areas of higher vulnerability. For the management of existing areas, it may be necessary to prioritize places of higher vulnerability for adaptation measures because those locations may require more intensive management. Areas of unique ecological or cultural value may continue to merit high priority. In addition to adaptation measures, substantial reductions in greenhouse gas emissions could enable the world to avoid the most serious consequences of climate change, which include global vegetation shifts and potential impacts on human well-being. Thank you very much.